Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillow, let your body settle into whatever position feels right. There's no rush, no urgency. Just this quiet moment, and the story we're about to share. Where in the world are you watching from tonight? A bedroom where the day has finally released its hold? A quiet corner where the world outside has grown still? Wherever you are, you're exactly where you need to be. Tonight, we're going to explore one of the most profound mysteries in modern astronomy. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has detected something that shouldn't exist. Galaxies so ancient, so impossibly old, that they appear to have formed before the universe itself had time to create them. We'll discover what these ancient light-bringers are telling us, understand why their existence challenges everything we thought we knew about cosmic history, and contemplate what it means when our most careful observations contradict our most trusted theories. It's a journey that spans the entire history of the universe, from the first fraction of a second after creation to the present moment, where we stand puzzled and amazed. But don't worry. This isn't going to be an anxiety-inducing crisis of cosmology. Instead, we'll move slowly and carefully through the science, the discovery, the puzzle, and the profound questions it raises. We'll explore the beautiful uncertainty at the heart of discovery, the patience required to understand the cosmos, and the peaceful acceptance that some of the most important questions don't have immediate answers. By the end, I think you'll find comfort in the vastness of what we don't yet know, and wonder in what we're learning to see. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps these videos reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting these quiet journeys into the unknown. So settle in now. Let your shoulders drop away from your ears. Take a slow breath in through your nose and let it go. Let your jaw relax, and let's begin our slow drift through time itself, back to the very edge of creation, where James Webb has found something that shouldn't be there. There's nowhere you need to be right now, nothing you need to solve. Just listen, and let the story of the universe's first light unfold around you like the darkness of space itself, infinite and full of stars. To understand what James Webb has found, we first need to understand what James Webb is. Not just a telescope, though it is certainly that. Not just a machine, though it's one of the most complex ever built. The James Webb Space Telescope is, in essence, a time machine, a device that lets us look backward through the history of the universe itself. Light, you see, takes time to travel. When you look at the sun, you're seeing it as it was 8 minutes ago, because that's how long it takes light to cross the distance between the sun and Earth. When you look at the nearest star beyond our sun, Proxima Centauri, you're seeing it as it was over 4 years ago. The light that reaches your eyes tonight left that star when you were 4 years younger. Look at a distant galaxy. And you might be seeing light that began its journey when dinosaurs walked the Earth, or when the Earth itself was forming, or before the Earth existed at all. James Webb was designed to see farther than any telescope before it, to catch the light from the very first stars and galaxies, the ones that formed in the ancient universe when everything was young and new. To do this, it needed to be enormous. Its primary mirror is over 21 feet across. Made of 18 hexagonal segments of gold-coated beryllium, each one polished to extraordinary precision. It needed to be cold, colder than you can easily imagine, because it observes in infrared light the heat signature of the universe, and it needed to be far from Earth, positioned at a point in space called L2, nearly 1 million miles away, where it orbits the Sun in perfect synchronization with our planet. The telescope launched on Christmas Day, 2021. Aboard an Ariane 5 rocket. For a month, it travelled through the darkness, unfolding like an impossibly complex origami sculpture. Its sun shield, the size of a tennis court, deployed layer by delicate layer. its mirror segments aligned with microscopic precision, and finally, in the cold silence of space, it opened its golden eye and began to see. What it saw was not just distant, it was ancient. Because when you look across vast distances in space, you're also looking backward through vast stretches of time. The light James Webb collects left its source billions of years ago, when the universe was young, when the first stars were just beginning to shine, when galaxies were forming in the primordial dark. The telescope doesn't just show us distant objects, it shows us the universe's own history, written in light that has been travelling toward us since before our solar system existed, before our galaxy had taken its current shape, before anything we would recognise as familiar had yet come to be. And in those first images, in that ancient light captured after travelling for billions of years, James Webb found something that shouldn't exist, something so old that it predates our understanding of when such things could form. Which brings us to the heart of our mystery, and to the question that keeps cosmologists awake at night, staring at their data in wonder and confusion. The first images from James Webb arrived in July 2022, and they were breathtaking. Galaxies swirled in deep space, their light stretched and reddened by the expansion of the universe. Nebulae glowed with the chemistry of creation, stars being born, stars dying, the universe in all its ancient vast complexity. But it was what astronomers saw when they looked carefully at the most distant galaxies that started raising eyebrows. These weren't just old galaxies, far away in space and time. These were galaxies that appeared too mature, too massive, too well developed for how early in cosmic history they existed. They had structure, they had mass, they showed signs of having already lived full, complex lives, when according to our timeline of the universe they should have barely begun to form. Redshift is how we measure cosmic distance and age. When light travels through expanding space, it gets stretched out, like a sound wave from a siren moving away from you. The wavelength gets longer, shifting toward the red end of the spectrum. The more the universe has expanded during the light's journey, the more redshift we see. High redshift means great distance and great age. We're seeing the object as it was in the distant past. James Webb started finding galaxies with redshifts of 10, 11, 12, even 13. These are galaxies we're seeing as they existed when the universe was less than 400 million years old. Some appear to exist just 200 million years after the Big Bang itself. In cosmic terms, this is extraordinarily early. The universe at that point was an infant. The first stars had only just begun to shine, burning away the hydrogen fog that filled all of space. This era is called the Cosmic Dawn. When light first pierced the darkness that followed the Big Bang, finding galaxies from this era wasn't surprising. That's what James Webb was built to do. What was surprising, what sent ripples of confusion and excitement through the astronomical community was what these galaxies looked like. They weren't small and simple and primitive, the way infant galaxies should be. They were massive. Some contained as many stars as the Milky Way galaxy contains today, billions upon billions of suns. They had structure, spiral arms, central bulges. They showed signs of having formed stars rapidly and efficiently. They looked, in short, far older than they had any right to be. This presented a problem, a genuine puzzle that cut to the heart of our understanding of cosmic history. Galaxies don't form instantly. They require time. Stars must first form from clouds of hydrogen and helium. Those stars must live out their lives, fuse heavier elements in their cores, and die, spreading those elements into space. New generations of stars must form from that enriched material. Dark matter must pull everything together through gravity's patient work. All of this takes time, hundreds of millions of years at minimum. And yet here were galaxies that seemed to have accomplished all of this in what cosmologists considered impossible time frames. It was as if finding a fully grown oak tree in a forest that had only existed for a week. The tree needs time to germinate, to grow, to develop its complex structure. You can't rush it, and yet there it stands, ancient and massive in a forest that shouldn't be old enough to contain it. And this is where the mystery truly begins. Where our most powerful telescope, our most careful observations, our best data all point to something that contradicts what we thought we knew about the universe's history, which leads us to examine what we thought we knew and to understand the timeline we've been working with, the story of the universe we've been telling ourselves for decades. Our current understanding of the universe begins with a moment of creation so brief, so violent, so transformative that it's hard to truly grasp. The Big Bang, we call it, though that name is somewhat misleading. It wasn't an explosion in space. It was the beginning of space itself, and time, and everything that would ever exist. 13.8 billion years ago, as precisely as we can measure, everything began. In the first fraction of a second, the universe expanded from something smaller than an atom to something larger than a galaxy. Space itself inflated at speeds that dwarf the speed of light. This is called cosmic inflation. And it solved several puzzles about why the universe looks the way it does, smooth and uniform on the larger scales. Then inflation ended, and the universe settled into a slower expansion that continues today. For the first few minutes after the Big Bang, the universe was unimaginably hot and dense, a sea of pure energy and fundamental particles. As it expanded and cooled, those particles began to combine. Protons and neutrons formed. Then, in those first precious minutes, the lightest atomic nuclei formed through nuclear fusion. Hydrogen and helium with trace amounts of lithium. This is called Big Bang nucleosynthesis, and it determined the chemical composition of the universe for hundreds of millions of years to come. 3/4 hydrogen, 1/4 helium. Almost nothing else. Then came an era of darkness. The universe was still too hot for atoms to form. Electrons couldn't attach to those nuclei without being immediately knocked away by the intense radiation filling all of space. This meant light couldn't travel freely. The universe was opaque, a fog of charged particles that scattered light in every direction. This lasted for roughly 380,000 years, a long wait in cosmic terms. When the universe finally cooled enough for atoms to form, light was suddenly free to travel. This moment is called recombination, and the light from that era still fills the universe today. We call it the cosmic microwave background radiation. And it's the oldest light we can see, a baby picture of the universe, showing it as it was just 380,000 years after creation. Before that, there is only darkness, impossible to observe directly. After recombination came the Dark Ages, and the name is literal. The universe was full of neutral hydrogen gas, but no stars had yet formed to light it up. Gravity was pulling matter together, collecting it into dense clouds, but the first stars had not yet ignited. This period lasted for perhaps 100 million years, though the exact timing is uncertain. The universe was dark, patient, waiting for gravity to finish its work. Then, somewhere between 100 and 200 million years after the Big Bang, the first stars formed. These were not like the stars we see today. They were massive, hundreds of times the mass of our sun, burning at ferocious temperatures, living fast and dying young in spectacular supernovae. They were made purely of hydrogen and helium. No heavier elements yet existed. We call them population 3 stars, and we've never actually observed one. They died long ago, but their legacy is the heavier elements they created and scattered into space. These first stars began to change everything. Their ultraviolet light started breaking apart the hydrogen fog that filled space, ionizing it, making it transparent. This is called reionization, and it's the process that made the universe clear enough for light to travel freely, for galaxies to become visible. According to our models, this process took time, perhaps several 100 million years, with early galaxies gradually clearing bubbles of ionized space around themselves, until those bubbles merged, and the universe became fully transparent. And it's in this timeline, this carefully constructed story of cosmic evolution, that James Webb's discoveries cause problems. Because the massive mature galaxies it's finding existed during or even before rare ionization, they appear to have formed when the universe was still in its infancy, still in the process of becoming what it would later be. Which raises the question that brings us deeper into this mystery. The question that we must now contemplate carefully and thoroughly. Imagine you're an archaeologist and you've developed a detailed timeline of human civilization. You know when agriculture began, when cities first arose, when writing was invented. Your timeline is based on careful study, multiple lines of evidence, decades of painstaking work. Then one day, you discover a smartphone buried beneath a layer of rock that dates to 10,000 years ago, long before electricity, before metallurgy, before written language. That smartphone shouldn't exist in that layer. It contradicts everything you know about the development of technology. This is, in essence, what cosmologists are facing with James Webb's observations. The galaxies themselves aren't in question. They're real. They're there. The telescope is seeing them clearly. What's in question is how they got there so quickly, how they became so massive and mature when the universe had barely had time to form stars, let alone organize those stars into vast gravitational structures containing billions of suns. Consider the process of galaxy formation according to our standard model. First, dark matter, which makes up most of the universe's mass, begins to clump together under its own gravity. This creates gravitational wells, pockets of space where matter accumulates more easily. Regular matter, the hydrogen and helium from the Big Bang, falls into these wells. It collects, it heats up from compression, and eventually it becomes dense enough for stars to form. Those first stars live and die, some exploding as supernovae, scattering heavier elements into space. A second generation of stars forms, made from material enriched with carbon, oxygen, iron, all the elements created in the cores of the first stellar generation. More stars form, more die, the galaxy grows. Stars gather into larger structures. Proto-galaxies merge with other proto-galaxies, drawn together by gravity. Over hundreds of millions of years, maybe a billion, you get a mature galaxy with structure, with billions of stars, with the spiral arms and central bulges we recognize. This process has a speed limit, not from the laws of physics, but from the simple fact that stars take time to form and die. You can't create heavy elements without stars living their full lives first. You can't form It's a cascade that simply cannot happen faster than a certain rate. And yet the galaxies James Webb is observing appear to have done exactly that. They seem to have compressed what should be hundreds of millions of years of evolution into just a couple 100 million years. Some appeared to exist just 200 million years after the Big Bang, given that the first stars probably didn't form until around 100 million years after the Big Bang. This gives these galaxies perhaps 100 million years to go from first starlight to massive, mature galactic structures. It's not impossible in the strict sense, but it's extraordinarily difficult to explain within our current understanding. Several specific galaxies illustrate the problem beautifully, or perhaps frustratingly. One, catalogued with the unwieldy designation Glass Z13, appeared to have a redshift of 13.1, placing it just 300 million years after the Big Bang. Another, CEERS-93316, seemed even older, with initial estimates suggesting it existed 235 million years after creation. These galaxies weren't just distant, they were bright, suggesting they contained enormous numbers of stars. They had mass, billions of times the mass of our Sun. They showed structure and organization. Some researchers calculated that to form such massive galaxies so quickly, stars would need to have formed with almost perfect efficiency, converting nearly all available gas into stars far more rapidly than we observe in any modern galaxy. The universe would need to have been far more efficient at making galaxies in its youth than it is today, which seems backward. Young systems are usually messy, inefficient, still learning. Old mature systems are the ones that have optimized their processes. This tension between observation and theory, between what we're seeing and what we expected to see, is where genuine scientific excitement lives. Because when your observations contradict your theories, one of two things is true. Either your observations are wrong, or your theories are incomplete. And discovering which one is the beginning of understanding something new about how the universe actually works. Before we go further, it's worth considering the most straightforward explanation for these impossible galaxies. What if they're not as old as we think? What if our measurements are wrong, and these galaxies are actually much younger, giving them plenty of time to form and grow? This is not a dismissal of the data. This is how science works, checking your measurements, questioning your assumptions, making sure the impossible is actually impossible before you start rewriting theories. Redshift is our primary tool for measuring cosmic distance and age, and while it's remarkably reliable, it's not infallible. When we observe a galaxy, we look at specific wavelengths of light emitted by known elements. Hydrogen emits light at very specific wavelengths, signatures as unique as a fingerprint. In a distant galaxy, those wavelengths are shifted toward the red end of the spectrum by the expansion of space. By measuring how much shift has occurred, we can calculate how much the universe has expanded since that light was emitted, which tells us how far away the galaxy is and how long ago we're seeing it. But there's a potential complication. What if what we're interpreting as redshift is actually something else? What if some of the light has been absorbed or altered by dust, making the galaxy appear more distant than it truly is? This is called photometric redshift, estimating distance from the brightness and colour of light, and it can occasionally be fooled. The gold standard is spectroscopic redshift, where you spread the light into a spectrum and directly measure the shifted wavelengths of specific emission lines. This is much more accurate, but also requires more telescope time and brighter sources. Many of the initial James Webb discoveries relied on photometric redshift. Astronomers would see a galaxy that looked very red, calculate its probable distance based on that redness, and publish their findings. In some cases, follow-up spectroscopy revealed that the galaxy wasn't quite as distant as first thought. The record holder for most distant galaxy has changed several times as measurements were refined. Some galaxies that initially appeared to break the timeline turned out to be merely very distant, not impossibly distant. This process of refinement is healthy and normal. Science is not about getting everything right the first time. It's about making observations, forming hypotheses, testing them rigorously, and adjusting your understanding when new data arrives. Some of those early, shocking distance measurements didn't hold up under scrutiny. The universe didn't need rewriting for those particular galaxies. But here's the important part. After the dust settled, after careful spectroscopic measurements, after the most questionable candidates were removed from consideration, there were still galaxies that remained stubbornly impossible. Still galaxies at redshifts of 10, 11, 12, confirmed through multiple methods, checked and rechecked, that appeared too massive and too mature for their age. The mystery didn't disappear with better measurements. It became more carefully defined, more precisely puzzling. One particularly well-studied example is a galaxy designated Jade's GSZ 14-0. Spectroscopic observations confirmed its redshift at 14.3, placing it just 285 million years after the Big Bang. It's bright enough to suggest it contains hundreds of millions of stars. The measurement is solid, the distance is certain, the age is not in dispute. And yet it exists in a time frame that makes its formation difficult to explain. This brings us to a crossroads in our exploration. We've established that James Webb is seeing truly ancient galaxies. We've confirmed they're as distant and old as we think they are. We've verified that they appear more massive and mature than our standard models predict. The observations are solid. The timeline problem is real. Which means we need to look more carefully at our theories, at our understanding of how galaxies form, at the assumptions we've made about the early universe. Because if the observations are correct, and we have good reason to believe they are, then something in our story of cosmic evolution needs adjustment. We need to understand not just what we're seeing, but why our models fail to predict it. We need to examine the foundations of cosmology itself, the assumptions we've built our understanding upon, and that examination, that careful questioning of everything we thought we knew, is what we'll explore as we continue deeper into this cosmic mystery, where the universe itself seems to be telling us that it's stranger and more surprising than we had imagined. To understand how galaxies could form faster than we expected, we need to talk about the invisible architecture of the universe, dark matter, the mysterious substance that makes up 85% of all matter in the cosmos, yet doesn't emit, absorb, or reflect any light whatsoever. We can't see it directly, but we know it's there because of how it affects everything we can see. And it's the key to understanding how galaxies form at all. Imagine the early universe as a vast cloud of hydrogen and helium gas, still hot from the Big Bang, expanding in all directions. Left to itself, this gas would simply spread out evenly, becoming thinner and thinner as the universe grew larger. There would be no stars, no galaxies, no structure at all, just an increasingly diffuse fog of atoms drifting through empty space. But that's not what happened. Because the universe wasn't left to itself. Dark matter was there from the beginning, invisible but influential, shaping everything through the force of its gravity. Dark matter doesn't interact with light or normal matter, except through gravity, but that single interaction is profound. In the early universe, dark matter began to clump together under its own gravitational attraction. Small density fluctuations, tiny variations in how evenly it was spread out, became seeds for larger structures. Denser regions pulled in more dark matter, becoming denser still. These clumps created gravitational wells, pockets of space where everything nearby began to fall inward. Regular matter, the hydrogen and helium we can actually see, fell into these wells that dark matter had created. As it fell inward, it gained speed. As it compressed, it heated up. And when it became dense enough and hot enough, stars began to form. The dark matter provided the scaffolding, the invisible framework that normal matter could arrange itself around. Without dark matter, without those gravitational wells to fall into, galaxies simply wouldn't exist. The universe would be empty and dark and profoundly lonely. This is the standard story of galaxy formation, what's called the hierarchical model. Small structures form first, proto-galaxies just a few million stars clumped together. These merge with other small structures, growing larger. Larger structures merge with each other, forming still larger ones. It's a bottom-up process, small to big, simple to complex, taking time and patience. And the speed of this process is limited by how quickly dark matter can clump together and create those gravitational wells deep enough to hold onto gas and form stars efficiently. But what if dark matter behaved differently in the early universe? What if it clumped together faster, created deeper gravitational wells sooner, pulled normal matter together more efficiently? This is one possible explanation for the massive early galaxies James Webb is observing. Perhaps our models of dark matter are incomplete. Perhaps it's not quite as simple as we thought. Most of our understanding of dark matter comes from studying the universe as it is today, billions of years after the Big Bang. We observe how galaxies rotate, how galaxy clusters hold together, how light bends around massive objects. All of this tells us dark matter exists and gives us clues about its properties. But we've never directly observed how dark matter behaved in the first few 100 million years after creation. We've extrapolated backward, assumed it behaved the same way then as it does now. Maybe that assumption needs refinement. Some cosmologists have suggested that dark matter might have had interactions with itself in the early universe that it doesn't have today. If dark matter particles could collide and transfer energy, they might have been able to dissipate energy as heat, allowing them to settle into concentrated clumps faster than non-interacting particles could. This could have created deeper gravitational wells earlier giving galaxies a head start on formation. Others have proposed that dark matter might not be a single thing, but rather multiple types of dark particles with different properties. Perhaps some dark matter is cold, moving slowly, clumping together easily, while other dark matter is warm, moving faster, resisting clumping. The ratio of cold to warm might have been different in the early universe, affecting how quickly structure formed. These are speculative ideas, explorations of possibility rather than confirmed theories, but they illustrate something important about scientific progress. When observations surprise us, we examine our assumptions. We ask what might be different, what we might have missed, what variations in the standard model could account for what we're seeing. And dark matter, invisible and mysterious, is a natural place to look for such variations, because we know so little about it to begin with. Another way to form massive galaxies quickly is to make them extraordinarily efficient at turning gas into stars. In the modern universe, this process is actually quite wasteful. When a cloud of gas begins to collapse under its own gravity, only a small fraction, typically 1 or 2%, actually ends up becoming stars. The rest gets heated up and blown away by stellar winds, or pushed out by radiation pressure from newly formed stars, or prevented from collapsing by magnetic fields threading through the cloud. Star formation in today's universe is an inefficient process. But what if the early universe was different? What if those first generations of stars formed with much higher efficiency, converting 10, 20, even 50% of available gas directly into stars? This would dramatically speed up galaxy formation, allowing massive structures to assemble in a fraction of the time our models typically allow. There are physical reasons why this might have been the case. The gas in the early universe was pristine, composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements. This is significant because heavier elements play a crucial role in modern star formation. When gas clouds collapse, they heat up. For the collapse to continue, the heat needs to be radiated away into space. Heavier elements, things like carbon and oxygen, are very efficient at radiating heat. They act like cosmic radiators, cooling the gas and allowing it to continue compressing until it's dense enough for stars to form. But in the early universe, without many heavy elements, this cooling process would have been less efficient. You might think this would make star formation harder, and in some ways it did. But it also meant that when gas clouds did collapse, they tended to form very massive stars, hundreds of times the mass of our Sun. These massive stars burn incredibly hot and bright, live fast lives, and die in spectacular supernovae that enrich the surrounding space with heavy elements. A single generation of these massive stars could have seeded the early universe, with enough heavy elements to make subsequent star formation much more efficient. There's also the question of how easily gas could cool and settle into the dense centres of dark matter halos. In computer simulations of galaxy formation, scientists model how gas falls into gravitational wells, how it swirls around, how it cools and condenses and eventually forms stars. These simulations have many adjustable parameters, knobs and dials representing physical processes we don't fully understand. How efficiently does gas cool? How much is heated and expelled by supernova explosions? How much is consumed by black holes forming at the centres of galaxies? When you adjust these parameters to match observations of modern galaxies, you get values that produce the slow, steady star formation we see today. But those parameters might have been different in the early universe. The gas might have been able to cool more quickly, fall into galactic centres more easily, form stars more rapidly. If you adjust the efficiency parameters in simulations of early galaxy formation, you can produce massive galaxies in shorter time frames. The question is whether those adjustments are physically realistic or just mathematical tricks to make the models match observations. One intriguing possibility involves the first supermassive black holes. We know that most large galaxies, including our own Milky Way, have enormous black holes at their centres, millions or even billions of times the mass of the Sun. These black holes can affect star formation in complex ways, sometimes suppressing it by heating gas, sometimes triggering it by compressing gas through powerful jets and winds. If supermassive black holes formed very early in cosmic history, earlier than we typically assume, they could have influenced the formation of their host galaxies in ways we haven't fully accounted for. James Webb has actually observed some very distant quasars, brilliant beacons powered by supermassive black holes, existing when the universe was less than 1 billion years old. The black holes powering these quasars are already billions of times the mass of the Sun. How they grew so large so quickly is its own mystery, related to but distinct from the galaxy formation problem. But their presence suggests that black holes and galaxies might have co-evolved more rapidly in the early universe than our models predict. All of these factors, the efficiency of star formation, the role of heavy elements, the cooling of gas, the influence of black holes, they're interconnected in complex ways. Changing one affects all the others. Understanding how they work together in the early universe requires not just observations, but sophisticated models and simulations. And what those models are beginning to suggest is that the early universe might have been a far more vigorous, energetic place than we realized, where stars formed in great bursts, where galaxies assembled with surprising speed, where the cosmic dawn was brighter and more active than we had imagined. There's another possibility we need to consider, one that's more fundamental and perhaps more unsettling. What if the laws of physics themselves were different in the early universe? Not different in a random way, but different in specific calculable ways that we haven't yet fully understood. This isn't science fiction. This is serious cosmology exploring the edges of the known. The universe has changed profoundly since the Big Bang. Its temperature has dropped from unimaginable heat to the cold darkness we see today. Its density has decreased as space itself has expanded. The particles that fill it have changed from a soup of quarks and gluons to the atoms and molecules we recognise. These aren't just environmental changes. They affect how fundamental forces operate, how particles interact, how energy flows from one form to another. In the first fraction of a second after the Big Bang, the 4 fundamental forces we observe today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were likely unified into a single force. As the universe cooled, this unified force split apart in a process called symmetry breaking, first gravity separating out, then the strong force, then the electromagnetic and weak forces diverging. Each of these separations represented a profound change in how the universe operated, a shift in the fundamental rules governing existence. Could there have been other transitions, other moments when physics shifted in ways we haven't fully mapped? Could the early universe have operated under slightly different rules, rules that permitted faster galaxy formation, more efficient star creation, processes that have no direct analogue in the universe we observe today? Consider dark energy, the mysterious force causing the universe's expansion to accelerate. We know dark energy exists because we can measure its effects, but we don't really know what it is or where it comes from. Current observations suggest it's been a constant presence throughout cosmic history, but what if it wasn't? What if dark energy was stronger or weaker in the early universe? This would have affected the rate of expansion, which in turn affects how easily matter can clump together under gravity. A period of slower expansion in the early universe could have given structures more time to form before being pulled apart by cosmic expansion. Or consider the cosmological constant related to dark energy, a term in Einstein's equations that represents the energy density of empty space itself. Einstein introduced it, then famously called it his greatest blunder, when observations seemed not to require it. But modern cosmology has brought it back. We need something like the cosmological constant to explain the universe's accelerating expansion. But the value we measure is incredibly small, far smaller than quantum physics suggests it should be. This discrepancy, called the cosmological constant problem, is one of the deepest puzzles in physics. What if its value has changed over cosmic time? What if it was different when those early galaxies were forming? These are not idle speculations. Physicists have constructed models, mathematical frameworks, that explore how varying fundamental constants or forces would affect cosmic evolution. Most of these models are constrained by observations. If the fine structure constant, which determines the strength of electromagnetic interactions, were significantly different, atoms wouldn't form properly. We can measure this constant in distant galaxies by looking at absorption lines in quasar spectra, and so far it appears to have been the same for billions of years. But the early universe, before most of our observation window begins, remains less constrained. There's also the possibility of fields we haven't discovered yet. Physics is full of fields, invisible influences that permeate all of space. The electromagnetic field, the gravitational field, the Higgs field that gives particles mass. Each field has associated particles, photons for electromagnetism, gravitons hypothetically for gravity, the Higgs boson for the Higgs field. What if there are other fields, other particles, that were important in the early universe but have since decayed away or become inactive? These could have affected how matter behaved, how quickly it clumped, how efficiently it formed stars. String theory, one attempt to unify quantum mechanics and gravity, suggests there might be many more dimensions than the three of space and one of time we experience. These extra dimensions are supposedly curled up so small we can't detect them, but in the extreme conditions of the early universe, they might have been more accessible, affecting physics in ways we don't see today. I want to be clear, these ideas are speculative. They're explorations of possibility, not established facts. Scientists pursuing these lines of thought are careful to ground them in mathematics and observation wherever possible. But they illustrate something important. The universe's history is long, and we've only directly observed a portion of it. Assuming that everything has always operated exactly as it does today might be an oversimplification. The impossible galaxies James Webb has found might be telling us that we need to think more carefully about the physics of the early universe, about how different conditions might have produced different outcomes, about the possibility that creation was stranger and more varied than our current models allow. The impossible galaxies aren't the only way the universe is confusing cosmologists right now. There's another problem, equally puzzling, called the Hubble Tension. And interestingly, these two mysteries might be related, might be symptoms of the same underlying gap in our understanding. The Hubble constant is a number that describes how fast the universe is expanding. It's named after Edwin Hubble, who in 1929 discovered that distant galaxies are moving away from us, and that more distant galaxies are moving away faster. This relationship between distance and recession speed is described by the Hubble constant. Know this number, and you can calculate the age of the universe, trace back expansion to the Big Bang, predict the fate of cosmic expansion far in the future. The problem is that we get different values for the Hubble constant depending on how we measure it, and the discrepancy is too large to be explained by measurement error. It's a real disagreement between two different ways of observing the universe, and it suggests that something in our cosmological model is incomplete or incorrect. One method of measuring the Hubble constant involves looking at the cosmic microwave background radiation, that ancient light from 380,000 years after the Big Bang. The pattern of tiny temperature variations in this radiation tells us about the density and composition of the early universe. Using our best models of how the universe evolves, we can extrapolate forward from that early snapshot to calculate what the expansion rate should be today. This method gives us a Hubble constant of about 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, roughly 3.3 million light-years, space is expanding at an additional 67 kilometers per second. The other method involves direct observation of the universe today. We measure the distances to nearby galaxies using various techniques, like Cepheid variable stars whose brightness fluctuates in predictable patterns, or Type 1a supernovae that all have similar intrinsic brightness. We measure how fast those galaxies are receding by looking at the redshift of their light. plot distance versus recession speed for many galaxies, and the slope of that line is the Hubble constant. This method gives us a value of about 73 kilometers per second per megaparsec. 67 versus 73 might not sound like a huge difference, but in cosmology it's significant. These measurements are precise, with error bars that don't overlap. Multiple independent teams using different instruments and techniques have confirmed both values. This isn't a matter of one measurement being wrong. Both appear to be correct, which means our model of the universe, the framework we use to connect the early universe to the modern universe, has something missing. One possible explanation is that the universe's expansion has not been as smooth and uniform as we assumed. Maybe there was a period of faster or slower expansion that our models don't account for. Maybe dark energy, the force driving accelerated expansion, hasn't been constant over cosmic time. Maybe it was weaker in the past and has strengthened, or vice versa. Another possibility involves the early universe being more complex than we realized. If there were additional forms of radiation or particles present in the early universe that have since disappeared, they could have affected expansion in ways not captured in our current models. This relates to the galaxy formation problem, because the expansion rate affects how easily matter can clump together under gravity. Faster expansion pulls things apart. Slower expansion gives gravity more time to work. Some cosmologists have proposed that both the Hubble tension and the early galaxy problem might be solved by revising our understanding of the first few 100 million years after the Big Bang. Perhaps this era was more eventful than we thought, with additional physical processes at work that our standard model doesn't include. Perhaps there were bursts of rapid star formation driven by processes we haven't identified. Perhaps dark matter clumped more efficiently than our models predict. Perhaps the expansion rate was different than we calculated. These mysteries are uncomfortable for cosmology, which has grown accustomed to remarkable agreement between theory and observation. For decades, our standard model of cosmology, called lambda CDM for the cosmological constant and cold dark matter, has successfully explained observation after observation. The cosmic microwave background matches predictions. The large-scale structure of the universe matches simulations. The abundance of light elements matches calculations from Big Bang nucleosynthesis. It's been a triumph of theoretical physics. But now we have cracks in that edifice. The Hubble tension, the impossible early galaxies. These aren't just minor discrepancies that can be explained away with tweaks to measurement techniques. They're genuine puzzles that suggest our understanding is incomplete. And while that might seem frustrating, it's actually exciting. Science progresses not when everything makes sense, but when careful observations reveal something unexpected. The universe is telling us something. We just need to listen carefully and figure out what it's trying to say. Underlying all of cosmology is an assumption so fundamental that we rarely examine it explicitly. It's called the Cosmological Principle, and it states that the universe, on large enough scales, is homogeneous and isotropic. In simpler terms, it looks roughly the same everywhere, and it looks roughly the same in all directions. There are no special places, no cosmic centres, no privileged directions. Every observer, anywhere in the universe, would see approximately what we see. This principle is not just philosophical. It's practical and testable. When we look at the cosmic microwave background radiation, we see tiny temperature variations, but the overall pattern is remarkably uniform. When we map the distribution of galaxies across the cosmos, we find structure, clusters and superclusters and vast cosmic webs, but averaged over large enough volumes the density is constant. The universe appears homogeneous and isotropic, just as the principle predicts. But what if it's not? What if we happen to live in a region of space that's unusual, more dense or less dense than average? What if the universe has large-scale structure that we haven't detected because we can only observe a finite volume, our cosmic horizon limiting our view? This would affect our interpretation of cosmic expansion, our measurements of the Hubble constant, our understanding of when and how galaxies formed. Imagine living on a hill and trying to understand the average elevation of your continent. If you assume you're at an average location, you'll get one answer. If you're actually on an unusually high plateau, your estimate will be wrong. The cosmological principle is essentially the assumption that we're not on a cosmic plateau, that our observable universe is representative of the whole. Most cosmologists believe this assumption is justified. We've looked in every direction and found no evidence of large-scale deviations from uniformity. The cosmic microwave background is uniform to 1 part in 100,000. Galaxy surveys show structure, but it averages out to uniformity on large scales. Everything points to the cosmological principle being correct. But there are subtle ways it could fail. Perhaps the universe has structure on scales larger than we can observe. Cycles of higher and lower density that average out over volumes bigger than our observable universe. We would see only 1 part of that cycle and mistake it for the whole. Or perhaps the universe is homogeneous on average, but with more variation than we thought. Maybe regions a few billion light-years across differ from each other by small but significant amounts, and we happen to be in an unusual region. If this were true, it would affect everything. Our distance measurements assume that objects of the same type, supernova for instance, have the same intrinsic brightness everywhere. But if cosmic expansion has been different in different regions, this assumption breaks down. Our calculations of the universe's age assume uniform expansion everywhere. Non-uniform expansion would change those calculations. Our understanding of when galaxies formed assumes they formed under similar conditions throughout the observable universe. But if conditions varied significantly from place to place, some regions might have formed galaxies earlier than others. There's even a more radical possibility. What if the cosmological principle is only approximately true, good enough for most purposes but breaking down in subtle ways that become important when you look at the very early universe? The first few 100 million years after the Big Bang were turbulent, with rapid changes in temperature, density and expansion rate. Perhaps this era was less uniform than we assume, with some regions evolving faster than others, some forming galaxies earlier, some remaining dark longer. This isn't to say the cosmological principle is wrong. The evidence supporting it is strong. But science progresses by questioning assumptions, especially when observations surprise us. The impossible galaxies, existing earlier than they should, might be telling us that the early universe was more varied and complex than our uniform models suggest. Or consider another angle. Our observations of the distant universe are always looking backward in time. When we see a galaxy at Redshift 13, we're seeing it as it was 13 billion years ago. We're not seeing what's happening there now. We can't. That light hasn't reached us yet. For all we know, the region of space where that early galaxy existed might be vastly different today, might have evolved along a different path than our local region. We're comparing apples and oranges, or rather, we're comparing our present to someone else's distant past, and assuming that past should look like our past at the same age. These are subtle points, philosophical as much as scientific. But they illustrate how much cosmology rests on assumptions that seem reasonable, but might not be strictly true. The universe is under no obligation to make itself easy for us to understand. It is what it is, and our job is to observe it carefully, question our assumptions gently, and build models that match what we actually see rather than what we expect to see. And what we're seeing, through the extraordinary vision of James Webb, is a universe that's more surprising than we anticipated, with implications that we're only beginning to explore. Let's pause here and consider what's actually happening in the astronomical community right now. Because the response to James Webb's puzzling observations is itself a beautiful illustration of how science works when confronted with the unexpected. There's no crisis, no panic, no declarations that everything we know is wrong. Instead, there's careful, systematic investigation, multiple teams independently checking results, healthy debate about interpretation, and genuine excitement about the possibilities. When the first impossible galaxies were reported, the immediate response was skepticism. Not dismissive skepticism, but the healthy scientific kind that asks, are we sure? Have we checked everything? Other teams obtained additional observations of the same galaxies, using different instruments and techniques. They measured spectra more carefully, looked for alternative explanations for the apparent high redshifts, checked whether dust or unusual stellar populations might be making young, nearby galaxies appear to be old, distant ones. In some cases, this scrutiny revealed that the initial interpretation was wrong. A few galaxies that seemed to be at impossibly high redshifts turned out to be much closer, their light altered by dust in ways that mimicked extreme distance. The record for most distant galaxy has changed several times as measurements were refined. This isn't embarrassing. This is science working as it should, self-correcting, becoming more accurate through iteration and peer review. But importantly, not all the impossible galaxies disappeared under scrutiny. A core of observations remained robust, galaxies that really do appear to be ancient and massive, that really do pose genuine puzzles for our models. And this is when science becomes truly interesting, when careful checking confirms that the surprising result is real, that nature is genuinely showing us something we didn't expect. The response has been multiple-pronged. Observational astronomers are obtaining more data, deeper observations of known early galaxies, wider surveys to find more examples, spectroscopic follow-up to confirm distances and study properties. Theorists are running new simulations, tweaking models of galaxy formation to see what parameters might allow faster growth. Specialists in dark matter physics are exploring whether modifications to dark matter properties could explain the observations. Cosmologists are examining whether changes to the expansion history or fundamental constants might help. This is not a single person or team working alone. It's hundreds of scientists across dozens of institutions and countries, each bringing different expertise, different perspectives, different tools to the problem. Papers are published, critiqued, refined. Conferences bring people together to share results and debate interpretations. Graduate students begin thesis projects investigating specific aspects of the mystery. It's a distributed, collaborative effort to understand what the universe is trying to tell us. And there's disagreement, which is healthy and necessary. Some researchers think the solution lies in better understanding star formation efficiency in the early universe. Others focus on dark matter. Still others believe we need to modify cosmological models more fundamentally. These aren't tribal camps refusing to listen to each other. They're different hypotheses being actively explored, with people following the evidence as they interpret it while remaining open to alternative explanations. What's not happening is anyone declaring with certainty that they have the answer, because honest science admits uncertainty. When faced with genuinely puzzling data, the correct response is not to immediately propose a grand new theory, but to investigate carefully, gather more information, test hypotheses rigorously, and see what survives scrutiny. Premature certainty is the enemy of understanding. There's also appropriate humility about how much we don't know. Our observations of the universe are limited by the sensitivity and resolution of our instruments. James Webb is extraordinary, but it can't see everything. There are distant, faint galaxies it can't detect. There are details of galaxy structure too small for it to resolve. We're looking at these ancient objects through a keyhole, seeing only the brightest, most obvious examples. The full population of early galaxies likely includes objects we're missing, and understanding the complete picture requires acknowledging these observational limits. The timeline of scientific progress is also important to remember. Major discoveries typically aren't explained immediately. Hubble's observation of cosmic expansion in the late 1920s wasn't fully understood until decades later, after the Big Bang theory was developed and confirmed. The cosmic microwave background radiation was discovered accidentally in 1965. But it took years of additional observations and theoretical work to understand its implications fully. Science is patient. It's willing to live with mystery while working steadily toward understanding. So when you see headlines about James Webb breaking cosmology or rewriting the universe, take them with appropriate skepticism. What's actually happening is more nuanced and more interesting. The telescope has found something genuinely puzzling. Scientists are responding with careful investigation, healthy debate, and appropriate uncertainty about what it means. This is not a crisis. This is discovery in action, the universe revealing itself to be more complex than our current models allow, and humanity rising to the challenge of understanding what we're seeing. It's a profoundly human endeavour, this quest to comprehend the cosmos, and watching it unfold in real time is a privilege that we should appreciate. Much of our understanding of galaxy formation comes not from direct observation alone, but from computer simulations. These simulations are extraordinary achievements, some of the largest and most complex calculations ever performed, running on supercomputers for months at a time, tracking the evolution of billions of particles representing dark matter and gas as they interact over cosmic history. They're our way of testing theories, of seeing what our equations predict when played forward from the Big Bang to the present. Here's how it works. You start with initial conditions representing the universe shortly after the Big Bang, a nearly uniform distribution of dark matter and gas with tiny density variations. You encode the laws of physics, gravity pulling matter together, pressure resisting collapse, gas cooling and heating, stars forming and dying. Then you let the simulation run forward in time, calculating how each particle affects every other particle, step by small step, watching as structure emerges from the initial smoothness. If your physics is right, if your initial conditions are accurate, the simulation should produce a universe that looks like the one we observe. It should form galaxies with roughly the right sizes, shapes, and distributions. It should produce the right number of stars, the right chemical composition, the right large-scale structure of cosmic webs and voids. When simulations match observations, it suggests we understand the underlying processes. When they don't, it tells us something needs adjustment. For decades, these simulations have been remarkably successful. They reproduce the large-scale structure of the universe beautifully. They form galaxies that look plausibly realistic. They match observed correlations between galaxy properties and dark matter halo masses. It's been a triumph of computational cosmology, evidence that our basic understanding of gravity, dark matter, and cosmic evolution is fundamentally correct. But they're not perfect, and they never claim to be. Simulations must simplify reality in certain ways because we can't possibly track every individual atom in a galaxy. Instead, we use particles that represent large collections of matter, and we use simplified rules to approximate complex processes like star formation and supernova feedback. These approximations, called subgrid physics because they handle processes smaller than the simulation's resolution, are necessary but uncertain. Different choices lead to different results. The formation of stars, for instance, is incredibly complex. It involves gravity, magnetic fields, turbulence, radiation pressure, chemistry, and more. We can't simulate all of this in detail across an entire galaxy, let alone across a cosmological volume containing thousands of galaxies. So instead, we use rules, recipes that say when gas is dense and cold enough, convert some fraction of it into stars at some particular rate. These recipes are calibrated to match observations of modern galaxies, but we don't know if they apply to the early universe. The same is true for supernova feedback, the process by which exploding stars heat gas and blow it out of galaxies. This prevents galaxies from converting all their gas into stars too quickly, which is important because observations show that most galaxies are inefficient star formers. But the details of how this works, how much gas gets heated, how far it gets ejected, how much falls back later, all of this involves subgrid physics that must be approximated. When simulations of the early universe don't produce massive galaxies as early as James Webb is observing them, it might mean our fundamental physics is wrong, but it might also mean our subgrid physics needs refinement. Our recipes for star formation and feedback need adjustment for early cosmic conditions. Distinguishing between these possibilities requires careful work. Recent efforts have focused on running simulations with different assumptions, exploring what happens if you make star formation more efficient, or reduce feedback strength, or modify how gas cools in the early universe. Some of these variations can produce earlier, more massive galaxies, bringing simulations closer to observations. The question is whether the required changes are physically motivated or just adjustments to make the model fit the data. There's an important philosophical point here about the relationship between simulation and reality. A simulation that matches observations doesn't necessarily mean we understand the underlying physics. It might mean we've found a set of approximations and subgrid rules that happen to give the right answer. Conversely, a simulation that doesn't match observations might not mean our physics is wrong. It might mean our approximations aren't capturing something important. This is why simulations and observations must work together, each informing the other. Observations tell us what the universe actually looks like, what needs to be explained. Simulations help us understand whether our theories can explain those observations, and they point toward what physical processes are most important. When simulations and observations disagree, it's a sign that we need either better observations, better simulations, or better theories, and often all three. The current situation with early galaxies is prompting a re-evaluation of simulation methods. Researchers are developing new subgrid prescriptions specifically for the early universe. They're running higher resolution simulations that can capture smaller scale processes. They're exploring alternative physics that might have been important in the first few 100 million years. And through all of this, there's an underlying humility about the limits of what simulations can tell us. They're tools, powerful and useful, but not oracles. They help us think through the implications of our theories, but they don't replace the need for observation and careful interpretation. The universe itself is the ultimate arbiter of truth, and our job is to listen to what it's telling us, adjusting our simulations and theories accordingly. Behind every scientific discovery are people, individuals with dreams and determination, working for years or decades to make the impossible real. The James Webb Space Telescope didn't spring into existence fully formed. It was conceived in the late 1990s, developed through the 2000s and 2010s, finally launching in 2021. That's more than 2 decades from initial planning to first light, and hundreds of people dedicated significant portions of their careers to making it happen. The telescope is named after James Webb, who administered NASA during the Apollo era, though there's been controversy about this choice given some aspects of his career. But setting aside the name, the instrument itself represents an extraordinary human achievement, the product of collaboration between NASA, the European Space Agency, the Canadian Space Agency, and thousands of engineers, scientists and technicians from multiple countries. Consider the challenges they faced. The primary mirror needed to be both enormous for light-gathering power and light to fit on a rocket. The solution was a segmented design, 18 hexagonal mirrors that fold for launch and unfold in space, each one individually adjustable to maintain perfect alignment. The material chosen was beryllium, a rare metal that's extremely stiff and holds its shape across temperature changes. Each segment was polished to incredible precision, their surfaces smoothed to within billionths of an inch, then coated with a microscopically thin layer of gold to optimize reflectance of infrared light. The sunshield presented its own challenges. It needed to be the size of a tennis court to block heat and light from the sun, earth and moon, keeping the telescope cold enough to detect faint infrared signals. But it also needed to fold small enough to fit inside a rocket. The solution was a multi-layer design. 5 sheets of special plastic film called Captain, each one about as thick as a human hair, separated by a vacuum to provide insulation. The layers are not taut like a drum. They're carefully designed to sag in specific ways that prevent heat from channeling through. Deploying all of this in space required over 300 single-point failure mechanisms, any one of which could have doomed the mission. Every hinge, every motor, every latch needed to work perfectly in the cold vacuum of space after months of travel from Earth. There was no possibility of repair. Unlike the Hubble Space Telescope, which orbits low enough for space shuttle missions to service it, Webb is too far away for human intervention. It had to work the first time. The engineers tested everything they could think of. They subjected components to vibration, to temperature extremes, to vacuum. They ran deployment tests hundreds of times. They developed backup procedures and contingency plans. But there was always uncertainty, always the knowledge that they couldn't test the actual flight hardware in actual flight conditions. Some things you only learn by trying. Launch day was Christmas 2021 from a spaceport in French Guiana. The Ariane 5 rocket performed flawlessly, releasing Webb on its journey to L2. Then began the most nerve-wracking month of the mission as the telescope gradually unfolded. The sun shield deployed, layer by layer. The mirror segments swung into position. Each step was monitored from mission control, each success celebrated with cautious optimism, and then it was done. The telescope was fully deployed, parked at its destination, beginning the process of cooling down and aligning its mirrors. Engineers spent weeks adjusting each mirror segment, using starlight to measure the alignment, making tiny corrections. Gradually bringing 18 separate mirrors into coherence as a single precise optical surface. When the alignment was complete, when the telescope achieved its design performance, there were tears in mission control. Years of effort, years of stress and doubt had culminated in success. The scientists who designed Webb's instruments also invested years of their lives. Each instrument, the cameras and spectrographs that analyze the light the mirror collects, represents its own engineering triumph. The near-infrared camera, NIR-CAM, can detect light from the very first stars. The near-infrared spectrograph, NIR-SPEC, can simultaneously measure spectra from hundreds of galaxies. The mid-infrared instrument, MIRI, operates at temperatures so cold that it requires its own dedicated cooling system. Each of these was designed by international teams, tested extensively, integrated carefully into the telescope, and now these instruments are providing data that's both confirming and surprising us. They're working beautifully, performing at or beyond their design specifications. The impossible galaxies we've been discussing aren't instrument errors or artifacts. They're real detections, carefully verified, representing genuine puzzles about cosmic history. The people who built Webb didn't know exactly what it would find. That's the nature of exploration. You build the best instrument you can, you point it at the most interesting targets, and you see what nature reveals. Sometimes it confirms your expectations, sometimes it surprises you, and when it does, when your creation shows you something impossible, something that challenges your understanding, that's when you know you've succeeded, that you've actually expanded the boundaries of human knowledge. Those engineers and scientists are now watching as their telescope rewrites our understanding of the early universe. It must be profoundly satisfying, and perhaps a little unsettling, to have succeeded so completely. Before we fully accept that these early galaxies are genuinely impossible, that they require new physics or revised cosmology to explain, we need to carefully consider more mundane explanations. Could these galaxies be ordinary objects that just appear unusual due to circumstances we haven't fully accounted for? This isn't skepticism for its own sake. This is good science, eliminating the ordinary before invoking the extraordinary. One possibility involves dust, those tiny particles of heavy elements that exist in galaxies and can affect the light we receive from them. Dust absorbs blue light more effectively than red light, a phenomenon called reddening. This is why sunsets are red. Earth's atmosphere scatters blue light away while red light passes through. Galaxies filled with dust appear redder than they would otherwise, and if you're not careful, you might mistake this reddening for cosmological redshift, thinking the galaxy is more distant than it actually is. Could the impossible early galaxies just be dusty nearby galaxies, misidentified as ancient distant ones? For some of the initial candidates, this turned out to be at least partly true. Careful spectroscopic observations revealed lower redshifts than photometric estimates suggested. The galaxies were still distant, but not impossibly so, giving them adequate time to form and evolve. This is why spectroscopy is the gold standard for measuring cosmic distances. It's much harder to fool than simple colour measurements. But dust can't explain all the observations. Many of the puzzling galaxies have confirmed spectroscopic redshifts. Their distances are certain. And while dust can make a galaxy appear redder, it also makes it appear dimmer by absorbing light. To appear as bright as these early galaxies do, even accounting for dust, they would need to be generating enormous amounts of light, which brings us back to the same problem of how they grew so massive so quickly. Another consideration involves gravitational lensing, the bending of light by massive objects. When light from a distant galaxy passes near a large galaxy cluster between it and us, the cluster's gravity bends that light, magnifying the distant galaxy and making it appear brighter than it would otherwise. This is a useful phenomenon that astronomers exploit to study distant, faint objects that would otherwise be invisible. But lensing could potentially create confusion. A lensed galaxy appears brighter, and if you don't account for the magnification properly, you might overestimate its intrinsic luminosity and therefore its stellar mass. Could the massive early galaxies be less massive than they appear, their brightness artificially enhanced by foreground lenses? For some galaxies, this is possible, and astronomers carefully model lensing effects when they're present. But many of the puzzling early galaxies aren't strongly lensed. They're observed in blank fields without obvious foreground clusters, and even for lensed galaxies, once you account for the magnification, they often still appear more massive than models predict for their age. There's also the question of stellar populations. The stars in a galaxy emit light at different wavelengths depending on their temperature, age, and composition. Young, hot stars are blue. Older, cooler stars are red. By studying the spectrum of light from a galaxy, astronomers can estimate what mix of stellar populations it contains, and from that, estimate its total stellar mass. But these estimates depend on assumptions about stellar physics, about how stars of different masses evolve and what light they emit at different ages. If there were unusual stellar populations in the early universe, stars with different properties than we observe today, our mass estimates could be wrong. Perhaps the early universe formed more extremely massive stars than we typically see, stars that burn incredibly bright but don't contribute as much mass as we'd estimate from their brightness. This is an active area of research, exploring whether population 3 stars, those first purely hydrogen and helium stars, might have had properties different enough from modern stars to significantly affect our interpretation of early galaxy observations. Some models suggest that if early galaxies were dominated by very massive stars, they could appear very bright while containing less total mass than we'd estimate using modern stellar population assumptions. None of these alternative explanations is necessarily wrong. Science progresses by considering multiple hypotheses and testing them against observations. As more data comes in, as we obtain deeper spectra and better characterize the properties of early galaxies, we'll be able to rule out some explanations and strengthen support for others. What's becoming clear is that while some mundane explanations can account for some of the observations, they likely can't explain all of them. There appears to be a genuine population of early massive galaxies that are challenging our models. Whether that challenge requires minor adjustments to our understanding, or more fundamental revisions, is still being determined. But the mere existence of alternative explanations doesn't mean the mystery is solved. It means we're doing science properly, considering all possibilities, letting the evidence guide us toward truth, rather than prematurely committing to any single interpretation. And that careful, methodical approach is how we'll eventually understand what James Webb is showing us. The story of early galaxies has a companion mystery, one that's equally puzzling and possibly related. James Webb and other telescopes have also detected supermassive black holes existing when the universe was very young, black holes so massive that they shouldn't have had time to grow to such enormous sizes. Understanding these ancient giants might help us understand the impossible early galaxies, because black holes and galaxies appear to have evolved together, influencing each other in ways we're only beginning to appreciate. A supermassive black hole is exactly what it sounds like. A black hole containing millions or billions of times the mass of the Sun, sitting at the centre of a galaxy and influencing everything around it. Our own Milky Way has one, a 4 million solar mass monster called Sagittarius A star, relatively calm and quiet right now, but capable of tremendous violence. Most large galaxies have such black holes at their hearts, and there appears to be a relationship between the mass of the central black hole and the properties of its host galaxy. The puzzle is how these black holes grew so large. Black holes form when massive stars collapse at the end of their lives, but stellar mass black holes are typically just a few to perhaps 100 times the Sun's mass. To grow from that to 1 billion solar masses requires accreting enormous amounts of matter, and accretion has speed limits. As matter falls into a black hole, it heats up and emits radiation, and that radiation pushes back on incoming matter, preventing it from falling in too quickly. This is called the Eddington limit, and it suggests there's a maximum rate at which black holes can grow. Even growing at the maximum Eddington limited rate, it takes hundreds of millions of years to grow 1 billion solar mass black hole from stellar mass seeds. And yet James Webb has observed quasars, which are supermassive black holes actively feeding and shining brilliantly, existing when the universe was less than 1 billion years old. Some have been found at redshifts of 7, 8, even 9, meaning they existed when cosmic age was measured in hundreds of millions of years rather than billions. This suggests one of several possibilities. Either black holes can somehow grow faster than the Eddington limit under certain conditions, violating what we thought was a fundamental constraint. Or black holes in the early universe started from much larger seeds than stellar collapse provides, perhaps forming directly from the collapse of massive gas clouds without going through a stellar phase first, or perhaps some combination of both, with primordial black holes that formed in the Big Bang's immediate aftermath serving as seeds that grew rapidly in the dense early universe. There's evidence for black holes influencing their host galaxies profoundly. When a supermassive black hole actively feeds, accreting matter and growing, it releases enormous amounts of energy. Some of this energy is emitted as intense radiation. Some is channeled into jets of particles moving at nearly the speed of light, beams that extend far beyond the galaxy itself. This energy can heat gas throughout the galaxy, preventing it from cooling and forming new stars. It can also trigger star formation in some circumstances by compressing gas clouds. This feedback between black hole and galaxy, this mutual influence, means they likely evolved together. Galaxies form stars. Some of those stars die and create stellar mass black holes. Those black holes merge and feed and grow into supermassive ones. Those supermassive black holes affect subsequent star formation, and the cycle continues. Understanding one aspect of this relationship might illuminate the other. If supermassive black holes formed very early and very quickly, they could have affected early galaxy formation in ways our models don't account for. Perhaps they heated gas and prevented it from forming stars in some regions, while concentrating it in others. Perhaps their jets stirred up the early universe, creating turbulence that affected how matter collected into galaxies. Perhaps the relationship between black hole mass and galaxy mass was different in the early universe than it is today. James Webb is providing new data on this relationship by observing both early galaxies and early active black holes simultaneously. Some of those massive early galaxies contain actively feeding supermassive black holes. Others don't seem to, or at least the black holes aren't bright enough to detect. This is revealing patterns, correlations between black hole activity and galaxy properties that might point toward how they influenced each other's growth. There's also the intriguing possibility that black holes might have been the catalyst that formed the first stars and galaxies. If primordial black holes existed, perhaps forming from density fluctuations in the very early universe, they would have served as gravitational anchors around which matter could collect. The first gas clouds might have collapsed around these black holes, forming the first stars in their vicinity, building the first proto-galaxies. This is speculative, but it illustrates how the mysteries of early galaxy formation and early black hole growth might be two aspects of the same puzzle. Solve one, and you might solve the other. Understand how galaxies formed so quickly, and you might understand how black holes grew so massive. Or vice versa. Understand black hole formation and growth, and the impossible early galaxies might become comprehensible. There's a subtle issue in astronomy that's worth considering as we think about these distant, ancient galaxies, the question of how we actually know how far away something is. Distance measurement in astronomy is surprisingly tricky, and all of our understanding of cosmic history rests on our ability to measure distances accurately. If our distance measurements are systematically wrong, everything else gets confused. For nearby stars within a few hundred light years, we can use parallax. This is the apparent shift in an object's position when you view it from different locations. Hold your finger in front of your face and alternate closing each eye, your finger appears to jump back and forth against the background. That's parallax. Do the same thing with a distant tree, and the shift is much smaller. The farther away something is, the less it shifts. For stars, we measure parallax by observing them 6 months apart, when Earth is on opposite sides of its orbit around the Sun, giving us a baseline of about 300 million kilometres. Even with this enormous baseline, the parallax of all but the nearest stars is tiny, measured in milliarc seconds, thousandths of an arcsecond. Where an arcsecond is 1/3600th of a degree, it requires extraordinarily precise measurements, but it works, and it gives us direct geometric distances to nearby stars. For more distant objects, we use what's called the cosmic distance ladder, a series of methods that build on each other. Cepheid variable stars whose brightness fluctuates in predictable patterns related to their intrinsic luminosity can be observed out to tens of millions of light years. If you can measure a Cepheid's period of variation, you know its true brightness, and by comparing that to how bright it appears, you can calculate its distance. Type 1. A supernova, exploding white dwarf stars that all reach roughly the same peak brightness, can be seen across billions of light years and serve as standard candles for measuring cosmic distances. But the calibration of supernovae depends on Cepheids, which depend on parallax measurements. Each rung of the ladder rests on the one below, and errors in the early rungs propagate upward. For the most distant object, galaxies billions of light years away, we primarily use redshift. The relationship between distance and redshift depends on the expansion history of the universe, which in turn depends on the universe's matter and energy content, dark matter and dark energy. So measuring the most distant objects requires assumptions about cosmology, creating a somewhat circular situation where we use cosmology to measure distances and use those distances to constrain cosmology. This circularity is broken by using multiple independent methods and checking for consistency. When different approaches give the same answer, we gain confidence. When they disagree, it signals a problem. The Hubble tension we discussed earlier is an example of such a disagreement. Different methods giving different values for the expansion rate, suggesting something in our understanding needs refinement. For the galaxies James Webb is observing, we're using spectroscopic redshift, which is quite reliable. We identify specific emission or absorption lines from known elements, measure how much they've shifted toward longer wavelengths, and calculate redshift directly from that shift. The uncertainty isn't in the redshift measurement itself, but in how we convert redshift to distance and age, which requires knowing the universe's expansion history. If the universe's expansion wasn't as smooth and regular as we assume, if there were periods of faster or slower expansion we haven't accounted for, then our redshift to distance conversion could be systematically wrong. A galaxy at redshift 13 might be slightly older or younger than we calculate depending on exactly how the universe expanded during the time its light was travelling toward us. But this uncertainty is relatively small, probably not enough to resolve the impossible galaxy problem. The observations are pushing against well-established frameworks. We're not talking about a factor of 2 uncertainty and age. We're talking about galaxies that appear to have formed perhaps 50 to 100 million years earlier than models predict. in a universe that's 13.8 billion years old. Small changes in the distance ladder or expansion history can't account for that. There's also the question of whether we're seeing typical galaxies or unusual ones. James Webb is incredibly sensitive, but it still has limits. It detects the brightest galaxies at high redshift, the ones producing the most light. There might be numerous faint early galaxies we're not seeing, and those could have very different properties. Our sample might be biased toward the most extreme objects, giving us a skewed view of what early galaxy formation was typically like. Astronomers account for this through statistical methods, estimating the total population of galaxies based on the ones we can detect, correcting for observational biases. But these corrections depend on assumptions about galaxy luminosity distributions and evolution, assumptions that might not hold in the early universe. So while we're confident the impossible galaxies are real and genuinely distant and genuinely puzzling, there are layers of measurement and interpretation involved in reaching that conclusion. Science is careful to acknowledge these layers, to understand where uncertainty creeps in, and to check everything multiple times using independent methods. And what all that checking is telling us is that the puzzle is real, that we're genuinely seeing something our models didn't predict, and that we need to think carefully about what it means. The history of astronomy is full of moments when observations forced revisions to theory, when the universe revealed itself to be different than we thought. These revisions are often gradual. Not sudden paradigm shifts, but slow accumulations of evidence that eventually tip the balance of scientific opinion. Understanding this history helps us appreciate the current situation with early galaxies as part of a larger pattern of discovery and revision. Consider the expanding universe itself, now such a fundamental part of our understanding that it's hard to imagine doubting it. But when Edwin Hubble first presented evidence that distant galaxies were receding from us, with more distant ones receding faster, it challenged the prevailing view of a static, eternal cosmos. Einstein himself had assumed the universe was static, even adding a cosmological constant to his equations to prevent them from predicting expansion or collapse. Learning that the universe was actually expanding, that it had a history and an age, required a profound shift in thinking. The Big Bang theory that emerged from this discovery wasn't immediately accepted. Fred Hoyle, who actually coined the term quote one as a derisive description, championed the steady-state theory, which proposed that the universe had always existed in roughly its current form, with new matter continuously being created to fill the voids left by expansion. This wasn't unreasonable. It was an elegant idea that avoided uncomfortable questions about cosmic origins. But observations, particularly the discovery of the cosmic microwave background radiation, eventually ruled it out. The universe had a hot, dense beginning, whether that made us philosophically comfortable or not. More recently, the discovery of dark energy and the accelerating expansion of the universe came as a complete surprise. Scientists measuring distant supernovae in the late 1990s expected to find that the universe's expansion was slowing down, decelerated by the gravitational pull of all the matter it contained. Instead, they found expansion was speeding up, as if some unknown force was pushing everything apart. This discovery was so unexpected that the researchers initially thought they'd made a mistake, checking and rechecking their data before reluctantly concluding it was real. Dark energy now accounts for about 68% of the universe's total energy content, yet we have essentially no idea what it is. It's simply the name we give to whatever is causing accelerated expansion. Similarly, dark matter, making up about 27% of the universe's mass, remains mysterious despite decades of searching for the particles that might compose it. We live in a universe where 95% of its content is stuff we don't directly understand, detected only through gravitational effects. These examples illustrate an important principle. The universe doesn't care about our theories. It is what it is, and our job is to observe it carefully and build models that match observations, adjusting those models when new data arrives. Sometimes adjustments are small, minor tweaks to parameters. Sometimes they're larger, requiring new components like dark energy or modifications to fundamental assumptions. The current situation with early galaxies might require either kind of adjustment. It might be that small changes to our models of star formation efficiency or dark matter behaviour can explain the observations without major conceptual shifts. Or it might be that we're missing something more fundamental about the early universe, some process or property we haven't yet identified. What's important is the spirit of inquiry, the willingness to follow evidence wherever it leads, even when it contradicts expectations. Scientists aren't defenders of established theories. They're explorers of reality, using theories as maps that are always subject to revision when new territory is discovered. There's also something deeply human about this process of revision and discovery. Each generation of astronomers believes it has a reasonably complete picture of the universe, and each generation is eventually humbled by observations that reveal how much remains unknown. We're likely no different. A century from now, astronomers might look back at our current understanding the way we look back at pre-Hubble cosmology, recognizing it as a step along the path, but incomplete in ways we can't yet see. This isn't a reason for despair or cynicism about scientific knowledge. Quite the opposite. It's a reason for appreciation of how much we've learned and excitement about how much remains to be discovered. Every answered question reveals new questions beneath. Every mystery solved exposes deeper mysteries. This is the nature of understanding a universe far larger and more complex than ourselves. The impossible galaxies James Webb has found are the latest chapter in this long story of discovery. They're puzzling us, challenging our models, forcing us to think carefully about our assumptions. And that's exactly what good observation should do. They should surprise us, stretch our understanding, push us toward a deeper comprehension. Whether the resolution comes through minor adjustments to existing theory or requires something more revolutionary, we'll be richer for the journey of figuring it out, for the careful thought and observation and debate that leads to understanding. There's a beauty to physics that goes beyond mere utility, beyond the practical ability to predict and explain natural phenomena. The equations that describe the universe, from Einstein's field equations of general relativity to the Schrödinger equation of quantum mechanics, possess an elegance that physicists find deeply satisfying. This aesthetic dimension of science is worth contemplating because it reveals something about how we relate to the cosmos intellectually and emotionally. Einstein famously said that the most incomprehensible thing about the universe is that it's comprehensible. That mathematics, a human invention or discovery depending on your philosophy, can describe the behaviour of galaxies and atoms with extraordinary precision is genuinely remarkable. The universe didn't have to be this way. It could have been chaotic, arbitrary, following no discernible rules. Instead, it follows laws that we can express in relatively compact mathematical form, laws that have held constant across billions of years and billions of light years. Consider the inverse square law of gravity, the observation that gravitational force decreases with the square of distance. Double the distance, and gravity becomes 1/4 as strong. This simple relationship describes how planets orbit stars, how galaxies cluster together, how the universe expands. It's mathematically elegant, and that elegance is not just aesthetic, it often points toward deep truth. Simple mathematical relationships tend to reflect fundamental physical principles, while complicated ad hoc formulas usually indicate incomplete understanding. When Einstein developed general relativity, he was guided partly by observational needs but largely by mathematical beauty. He wanted a theory that was geometrically elegant, that described gravity not as a force, but as the curvature of space-time itself. The equations he derived are complex, but they have a beauty to them, a coherence that suggested to Einstein and others that they were on the right track even before observations confirmed his predictions. Paul Dirac, one of the founders of quantum mechanics, famously said it's more important to have beauty in one's equations than to have them fit experiment, because if the equations are beautiful, they're likely revealing something true even if current experiments haven't caught up. This sounds almost mystical, this faith in mathematical beauty, but it's actually been a reliable guide in physics. Theories that are mathematically elegant have tended to survive and deepen, while ugly, complicated theories have tended to be replaced by simpler, more beautiful ones. What does this have to do with the impossible galaxies? Perhaps nothing directly. But it shapes how physicists think about the mystery. When observations don't match predictions, there's a tendency to seek explanations that preserve the elegance of existing theories, that require minimal ad hoc adjustments. This isn't stubbornness. It's experience-based wisdom that fundamental theories, the ones that describe nature at the deepest level, tend to be simple and beautiful. If explaining early galaxies requires adding complicated new processes, dozens of free parameters that can be adjusted to fit data but don't flow naturally from deeper principles, physicists will be unsatisfied even if the model technically works. They'll keep looking for simpler explanations, more elegant frameworks that make the observation seem natural rather than forced. Conversely, if an explanation emerges that's both simple and deep, that perhaps resolves not just the galaxy formation puzzle, but also other mysteries like the Hubble Tension or dark matter's nature, that reveals unexpected connections between phenomena we thought were separate, that will feel right in a way that goes beyond just matching observations. It will have that quality of inevitability that great scientific insights possess, the sense that of course it had to be this way. How could we not have seen it before? We're not there yet with the early galaxy mystery. No compelling elegant explanation has emerged that satisfies both the observations and physicists' aesthetic sense. This suggests we're in an intermediate phase, gathering data, exploring possibilities, not yet seeing the deeper pattern. But history suggests such patterns exist, waiting to be discovered. There's also poetry in the observations themselves, independent of equations. The fact that we can see light that has been travelling toward us for over 13 billion years, that we can catch photons that left distant galaxies when the universe was young and innocent, that we can reconstruct the history of cosmic evolution from these ancient messengers. This is profoundly beautiful in its own right. We're creatures who emerge from the universe attempting to understand that same universe. Stardust contemplating stars. We build telescopes and write equations and construct theories, and somehow, improbably, it works. We actually can understand, at least partially, the cosmos that created us. There's something almost miraculous about that. Something that should inspire wonder regardless of whether any particular theory proves correct. The impossible galaxies are part of this larger story, this human quest to comprehend creation. They're puzzling us right now, but that puzzle is itself beautiful, a challenge worthy of our best efforts, an invitation to think more deeply about time and space and matter and light. Whatever the eventual explanation, the journey toward it is enriching us, expanding our understanding, connecting us to the universe in profound ways. And that connection, that sense of participating in something larger than ourselves, is perhaps the deepest reward of scientific inquiry. One of the hardest lessons in science, and perhaps in life generally, is learning to live comfortably with uncertainty. We want answers, clear and definite, preferably immediately. But the universe doesn't always cooperate with our desire for certainty. Sometimes the honest answer to a question is quote two, and learning to accept that, to sit with the discomfort of not knowing while patiently working toward understanding, is a mark of intellectual maturity. The impossible galaxies James Webb has found present exactly this situation. We have good observations, we have multiple competing explanations, each with strengths and weaknesses. We don't yet know which explanation is correct, or whether the truth involves some combination of factors we haven't fully appreciated. And that's okay. That's where science often finds itself at the frontier of knowledge, in a space of productive uncertainty where possibilities are being explored, but nothing is yet settled. This uncertainty is different from ignorance or confusion. It's structured uncertainty, uncertainty that knows what it knows and what it doesn't, that has clear questions to answer and methods for answering them. It's the kind of uncertainty that drives progress rather than paralyzing it. Scientists working on the early galaxy mystery aren't throwing up their hands in despair. They're making observations, running simulations, testing hypotheses, gradually narrowing the range of possibilities. The public often has trouble with this kind of uncertainty. People want experts to be certain, to speak with authority, to provide clear answers. When scientists say, "We're not sure yet," or "There are several possibilities," it can sound like weakness or evasion. But it's actually honesty and integrity, an acknowledgement that science is a process, not just a collection of facts, and that process takes time. There's also a cultural dimension to how we handle uncertainty. Some philosophical and religious traditions embrace mystery as a fundamental aspect of existence, something to be accepted and perhaps celebrated rather than something to be eliminated through knowledge. Other traditions emphasize the possibility and importance of achieving certainty through reason or revelation. Science occupies an interesting middle ground, acknowledging mystery while working systematically to reduce it, comfortable with temporary uncertainty, but always pushing toward better understanding. The early galaxy mystery illustrates how science handles uncertainty productively. First, verify that the uncertainty is real, that the observations are solid, and the puzzle genuine. This has been done. Multiple teams using different methods have confirmed the basic observations. Second, enumerate the possible explanations, thinking broadly about what could account for what we're seeing. This is ongoing, with various hypotheses being explored. Third, determine what observations or calculations would distinguish between possibilities, and then do those observations or calculations. This is where we are now, gathering more data, running more sophisticated simulations, testing predictions. Fourth, and this is crucial, be willing to live with uncertainty while this process unfolds. Don't force premature conclusions. Don't let the discomfort of not knowing push you into accepting inadequate explanations just to have any answer. Be patient. Be thorough. Let the evidence accumulate and point toward truth in its own time. This might take years. It might take decades. The nature of dark matter has been uncertain for nearly a century, since Fritz Zwicky first inferred its existence from the motion of galaxies and clusters. We still don't know what it is, despite decades of searching. This doesn't mean the search has failed. It means the answer is subtle, requiring patient investigation and perhaps waiting for the right experimental technique or theoretical insight to emerge. The early galaxy mystery likely won't take that long to resolve. The observations are recent, the field is active, progress is being made. Within a few years, we'll probably have a much clearer picture of what's happening, which explanations are holding up, and which are falling away. But even if it takes longer, that's acceptable. The universe has been here for nearly 14 billion years. It will wait while we figure things out. There's a certain humility required to live with uncertainty well, an acknowledgement that we don't automatically deserve to understand everything immediately, that the universe is under no obligation to make itself comprehensible on our preferred timeline. But there's also confidence that the methods of science, observation and reason and careful testing will eventually lead to understanding if we're patient and thorough. For those of us observing this process from outside the scientific community, watching experts grapple with these mysteries, there's value in appreciating the uncertainty rather than being frustrated by it. These are profound questions about the universe's history and nature. They deserve careful thought and thorough investigation. Quick, confident answers would likely be wrong. Slow, uncertain progress toward truth is far more valuable. And in the meantime, in this space of not fully knowing, there's room for wonder, for contemplation, for appreciating the mystery itself as a kind of gift. The universe is revealing itself to be more surprising than we expected, and that's marvellous, worthy of patient curiosity rather than anxious demand for immediate explanation. So we wait, and we watch, and we think, and gradually, slowly, understanding deepens. let's allow ourselves to imagine, carefully and scientifically, what the first light in the universe actually looked like, what it would have been like to witness the cosmic dawn if such witnessing were possible. This isn't fantasy. This is extrapolation from our best understanding, a thought experiment grounded in physics, allowing us to appreciate the profound transformation that occurred when stars first ignited in the primordial dark. The universe after recombination, after atoms formed and light could travel freely, was not quite dark. The cosmic microwave background radiation filled all of space, the afterglow of the Big Bang itself. But this radiation was visible light then. Not the microwave frequencies we detect today. The universe glowed a dull red, like the fading embers of a cosmic fire, gradually cooling and dimming as space expanded and stretched those wavelengths longer and longer. But there were no point sources of light, no stars, no galaxies, no bright beacons in that fading glow, just a uniform redness slowly shifting toward infrared and then beyond, into wavelengths our eyes couldn't see. And then, darkness. The Dark Ages, when the universe was filled with neutral hydrogen gas but nothing yet shined. Somewhere, everywhere, gravity was working patiently, pulling matter together into denser clouds, collecting hydrogen into the gravitational wells that dark matter had created. These clouds grew denser, hotter, until finally, in the densest cores, pressure and temperature reached the point where nuclear fusion could ignite. Hydrogen nuclei overcame their mutual electrical repulsion and fused together, releasing energy, creating light. The first stars were born. These weren't gentle events. The first stars were massive, perhaps hundreds of times the sun's mass, and they burned with fierce intensity. Their surfaces would have been incredibly hot, tens of thousands of degrees, glowing brilliant blue-white. They would have been bright enough to light up vast volumes of space around them, their ultraviolet radiation beginning to ionize the hydrogen gas, creating bubbles of clarity in the fog. If you could have been there, impossibly, watching from some vantage point outside the universe's normal constraints, you would have seen lights appearing in the darkness, scattered at first, isolated stars burning alone in the primordial night. Then more, as gravity continued its work, as more clouds reached the threshold of fusion. The lights would have been blue, achingly blue, the colour of stars too hot for life, too violent for anything but the pure physics of fusion. And around each star, the hydrogen fog would have cleared, ionized by ultraviolet light, becoming transparent. Small bubbles of clarity at first, then growing, overlapping, merging. The universe would have transformed from opaque to transparent, from dark to illuminated, not all at once, but gradually, over hundreds of millions of years, as more stars formed and more bubbles grew, until there was no fog left, just clear space and brilliant blue stars scattered throughout. Some of those stars lived fast and died young, exploding as supernovae within just a few million years of igniting. These explosions would have been spectacular beyond imagining, briefly outshining entire regions of space, scattering heavy elements into the surrounding gas, seeding the universe with carbon and oxygen and iron, all the elements that would later make planets and life possible. Those explosions also compressed surrounding gas, triggering new rounds of star formation. The second generation of stars, made from material enriched by the first generation's deaths, would have been more diverse, ranging from massive blue giants to smaller, longer-lived stars more like our Sun. These second-generation stars began to cluster together, drawn by mutual gravity, forming the first proto-galaxies. And here's where the mystery we've been exploring enters the picture. According to our models, this process should have taken time, hundreds of millions of years for the first stars to form, then hundreds of millions more for those stars to die and enrich their surroundings, then more time still for second-generation stars to form and begin collecting into galaxies. The universe at 200 or 300 million years of age should have been full of isolated stars and small clusters, not large, mature galaxies. But James Webb is showing us those large, mature galaxies existing when the universe was young, suggesting that either our timeline is wrong or the process was more efficient than we realised. Perhaps stars formed in great bursts rather than gradually. Perhaps proto-galaxies assembled faster through unusually efficient mergers. Perhaps the first stars were so numerous and so violent that they accelerated everything that came after. Whatever the explanation, first light was transformative, a moment when the universe changed fundamentally from dark to illuminated, from simple to complex, from pure hydrogen and helium to an increasingly rich chemistry that would eventually allow for planets and life and consciousness. We're the descendants of that cosmic dawn, made of atoms forged in those early stars, observing the universe with consciousness that emerged from it, trying to understand our own origins written in light that has travelled toward us across cosmic time. James Webb is extraordinary, but it's not the end of our exploration of the early universe. It's the beginning of a new era of observation, and even more powerful instruments are being planned and built. Telescopes that will see even farther, even more clearly, potentially resolving the mysteries Webb has uncovered, while doubtless revealing new puzzles we haven't yet imagined. The next major space telescope is the Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer, who advocated for what became the Hubble Space Telescope. Roman is scheduled to launch in the mid-2020s and will have a field of view 100 times larger than Hubble's, allowing it to survey vast areas of sky efficiently. While it's designed primarily to study dark energy and exoplanets, its wide field will also capture enormous numbers of distant galaxies, providing statistical samples that complement Webb's deep, targeted observations. On the ground, extremely large telescopes are under construction that will dwarf anything currently operational. The European Extremely Large Telescope, with a primary mirror 39 metres across, is being built in Chile's Atacama Desert. The Giant Magellan Telescope, combining 7 mirrors for a total collecting area equivalent to a 24.5 metre telescope, is being constructed at the same site. The 30-metre telescope, facing various challenges but still planned, would join them as another giant eye on the cosmos. These ground-based telescopes will have advantages and disadvantages compared to space-based ones. They're limited by Earth's atmosphere, which blocks certain wavelengths and causes turbulence that blurs images. But they also have enormous light-gathering power thanks to their huge mirrors, and they can be upgraded with new instruments as technology advances, something that's impossible for a telescope 1 million miles away in space. One particularly exciting prospect involves adaptive optics, systems that measure atmospheric turbulence and adjust mirror shapes in real time to compensate, creating images as sharp as if the telescope were in space. These systems are becoming increasingly sophisticated, allowing ground-based telescopes to achieve resolution that rivals or exceeds space telescopes at certain wavelengths. For studying the detailed structure of distant galaxies, this could be transformative. There are also proposals for future space telescopes even more ambitious than James Webb. The Habitable Exoplanet Observatory, HABEX, would have a mirror 4 metres across optimised for finding and studying Earth-like planets around other stars. The Large Ultraviolet Optical Infrared Surveyor, LUVOIR, could have a mirror up to 15 metres across, dwarfing Webb's 6.5 metres, allowing it to see fainter, more distant objects with greater clarity. These proposed telescopes are decades away and might not be built in exactly the forms currently envisioned. Funding must be secured, technology must be developed. Political support must be maintained across multiple administrations. But they represent the direction of astronomical ambition, the drive to build ever more powerful tools for observing the universe. For the early universe specifically, there's interest in telescopes optimized for infrared observation, since light from the most distant galaxies is redshifted into infrared wavelengths. Webb pioneered this capability, but future instruments could push even further, detecting galaxies at redshifts of 15, 20, possibly higher, seeing ever closer to the Big Bang itself, to the era of first star formation, perhaps even glimpsing population 3 stars directly. There's also excitement about combining multiple telescopes to create interferometers with effective apertures far larger than any single telescope could achieve. The Event Horizon Telescope, which captured the first images of black hole shadows, demonstrated this technique for radio wavelengths, linking telescopes across the globe to create an Earth-sized virtual telescope. Doing something similar in infrared or optical wavelengths is more challenging but not impossible, and would provide resolution and sensitivity beyond anything currently imaginable. Beyond telescopes, future gravitational wave detectors might provide complementary information about the early universe. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory planned for the 2030s, will detect lower frequency gravitational waves than ground-based detectors can, potentially seeing signals from supermassive black hole mergers in the early universe. This would provide a completely different window on cosmic history, complementing electromagnetic observations. The point is that Webb's discoveries are not endpoints. They're provocations, challenges that will drive the development of new instruments and observational techniques. The impossible galaxies will be studied with greater precision as better tools become available. We'll accumulate more examples, better statistics, deeper understanding of their properties. We'll test different theoretical explanations against increasingly detailed observations, and each new instrument will likely surprise us with discoveries we didn't anticipate. That's the pattern of astronomical history. Every improvement in our ability to observe reveals phenomena we didn't expect. Hubble showed us deep fields teeming with distant galaxies when we thought space might be mostly empty. Planck mapped the cosmic microwave background with precision that tested cosmological models to their limits. James Webb is showing us impossible early galaxies. What will the next generation reveal? We don't know, and that's exciting rather than frustrating. The universe is far larger and stranger than we can currently comprehend, and each new window we open shows us vistas we couldn't have imagined. Our descendants, astronomers of the late 21st century or beyond, will look back at our current puzzlement about early galaxies the way we look back at pre-Hubble cosmology, as a necessary step in an ongoing journey of discovery. There's something profoundly disorienting about cosmic timescales, about trying to grasp the sheer age of the universe and what that age means. 13.8 billion years is not a number we can truly comprehend through direct experience. We live for decades, remember events from years or perhaps decades past, think of centuries as ancient history. But billions of years, billions with a B, that's a timescale that defeats intuition, that requires different ways of thinking to appreciate even partially. Consider what a billion years means. Modern humans, Homo sapiens, have existed for perhaps 300,000 years, a span that includes all of recorded history, all of civilization. Every human who has ever lived. A billion years is over 3,000 times longer than that entire span. If you compressed human history into a single day, a billion years would be more than 8 years. The universe has existed for over 13 such periods, an expanse of time that makes all of human experience vanishingly brief. Or consider this. The Earth is about 4.5 billion years old. That means the universe existed for over 9 billion years before our planet formed, before our solar system came into being. For most of cosmic history, 2/3 of it, Earth didn't exist. The Sun didn't exist. The Milky Way galaxy did exist, though it was younger and different in structure, still actively forming stars and growing through mergers with smaller galaxies. When we look at galaxies from the first few 100 million years after the Big Bang, we're seeing a universe that's profoundly different from our own in time as well as space. Those galaxies exist now, or at least they existed 13 billion years ago, and whatever they've become in the meantime. The light hasn't reached us. For all we know, they've long since merged with other galaxies, Their stars have died and been replaced. The universe has moved on. We're seeing ancient history, a snapshot of cosmic youth that no longer exists except in the light travelling toward us across vast emptiness. This creates a strange relationship between observation and existence. The galaxies we observe at high redshift are simultaneously real. We're seeing actual light from actual objects, and unreal, in the sense that what we're seeing is long gone, transformed by billions of years of evolution we can't see. We're cosmic archaeologists studying artifacts whose origins predate our existence by an enormous margin, trying to reconstruct history from incomplete evidence. There's also the humbling realization of cosmic synchronicity, or the lack thereof. When those first stars were igniting in distant regions of space, the matter that would eventually become our solar system was scattered diffusely in the Milky Way, just hydrogen and helium and trace amounts of heavier elements, not yet collected into the dense cloud that would collapse to form the sun and planets. By the time Earth formed and life emerged here, those distant regions had evolved through billions of years of their own history, forming countless stars, building complex structures we can barely begin to observe. We exist in a moment, or rather, we experience time as a succession of moments, each one present and real. But cosmically, there is no single now that spans the universe. Light takes time to travel, and what we see happened in the past, the distant past for distant objects. Two events separated by sufficient distance have no objective temporal order. There's no cosmic clock that tells us what's happening right now in a galaxy 13 billion light-years away, because now itself is not absolute, but depends on your frame of reference. Einstein's relativity teaches us this, that time and space are intertwined, that simultaneity is relative, that the universe doesn't have a single universal present moment, but rather a complex structure of space-time where every observer has their own perspective. For practical purposes at human scales this doesn't matter, but at cosmic scales it's fundamental. The universe we observe is a patchwork of different eras, nearby objects in the near past, distant objects in the deep past, all assembled into a single observational present that doesn't correspond to any single cosmic __, quote, _8, __. This has philosophical implications worth contemplating. What does existence mean if there's no universal present? Do those ancient galaxies still exist in some absolute sense, or do they exist only as information, as light-carrying news of their past states? Is the universe a four-dimensional structure, a block universe where past, present and future all exist equally, with our experience of flowing time being some kind of limitation of consciousness rather than a feature of reality itself? These questions don't have simple answers, and perhaps they're more philosophical than scientific. But they arise naturally when you think deeply about cosmic time, about what it means to observe the ancient universe, about the relationship between the local flow of time we experience and the vast, incomprehensible duration of cosmic history. The impossible early galaxies James Webb has found existed when the universe was very young, just 2 or 3% of its current age. They're among the earliest structures we can observe, close to the beginning in cosmic terms, though still billions of years after the Big Bang itself. Understanding them means understanding not just their physical properties, but their temporal context, their place in the enormous span of time between creation and the present moment. Wherever and whenever that present moment might be, there's something extraordinary about living in an era when we can ask questions about the early universe and actually expect to find answers. For most of human history, the origins of the cosmos were purely a matter of speculation, mythology, or philosophical reasoning. Ancient peoples created beautiful creation stories, narratives that gave meaning and order to existence, but had no way to test their accuracy against observation. Even when science began to develop systematic methods for understanding nature, the universe's history remained beyond reach, too remote in time and space to investigate empirically. That changed remarkably recently. The Big Bang theory was developed in the mid-20th century. The cosmic microwave background radiation, the strongest evidence for a hot, dense beginning, was discovered only in 1965. Before that, scientists debated whether the universe was eternal or had a beginning, whether it was static or expanding, with limited observational evidence to guide them. Within a single human lifetime, we've gone from fundamental uncertainty about the universe's nature to detailed knowledge of its history, composition, and large-scale structure. And now we have telescopes that can literally see the early universe, that can capture light from galaxies as they appeared just a few 100 million years after creation. This is not metaphorical. This is direct observation of cosmic history, looking backward through time by looking outward through space, seeing the universe's youth with our own instruments. It's a profound privilege, one we should pause to appreciate. Consider how unlikely it is that we exist at all, let alone exist at a time when such observations are possible. The universe had to evolve for billions of years to create the conditions for life. Stars had to form and die, enriching space with heavy elements. Planets had to coalesce from that enriched material. Life had to emerge, evolve complexity, develop intelligence. Civilization had to arise, develop technology, build telescopes. All of this required an enormous sequence of contingent events, any one of which could have failed to occur or occurred differently, preventing our existence. And the timing is significant. We exist in an era when the universe is old enough to have developed galaxies and stars and planets and life, but still young enough that we can see cosmic history. The universe's expansion means that distant galaxies are receding from us, and as they recede, their light gets redder, fainter, harder to detect. Eventually, in the far future, billions of years from now, the universe's accelerating expansion will have carried distant galaxies beyond our cosmic horizon, their light stretched to such long wavelengths and thinned to such low intensity that no telescope, no matter how advanced, could detect them. Hypothetical astronomers in that distant future, if any exist, would observe a universe that appears much smaller and lonelier than ours, a dark void with only their local group of galaxies visible. Hey, everything else having receded beyond observational reach. They wouldn't be able to see the cosmic microwave background. They wouldn't be able to measure the universe's expansion history. Much of what we currently know about cosmology would be impossible for them to discover. We live in a golden age of observational cosmology, when the universe is revealing its history to those with the technology and curiosity to observe. This won't last forever in cosmic terms. It's a brief window, and we're fortunate to exist within it, to be asking questions about first light in early galaxies and cosmic dawn, and to have the tools to begin answering those questions. This perspective doesn't diminish the importance of the questions we can't yet answer, the mysteries like the impossible early galaxies that challenge our understanding. If anything, it enhances their significance. We're not just solving abstract puzzles. We're uncovering the history of everything, the story of how the universe evolved from simplicity to complexity, from uniformity to structure, from a hot, dense state to the rich, varied cosmos we observe today. And there's something deeply satisfying about the pursuit itself, independent of specific answers. The process of wondering, of formulating questions clearly enough to investigate them, of developing instruments and methods to gather evidence, of thinking carefully about what that evidence means. This process connects us to the universe in profound ways. We're not separate from the cosmos we study. We're part of it, aspects of the universe becoming aware of itself, consciousness emerging from matter and energy to contemplate matter and energy. When we observe distant galaxies, we're seeing light that has travelled across the universe for billions of years, and that light is interacting with matter in our telescopes, in our detectors, eventually in our brains as we process the information. The universe is communicating with itself across vast spans of space and time, and we're privileged to be part of that communication, to receive those messages from the deep past and try to understand what they're telling us. The impossible galaxies are part of this larger conversation between present and past, between observation and theory, between curiosity and cosmos. They're challenging us, pushing us to think more carefully, to question our assumptions, to be humble about how much we don't know, while being confident in our ability to learn. And that challenge, that invitation to deeper understanding, is a gift we should receive gratefully, working patiently toward comprehension, while appreciating the wonder of the mystery itself. After this long journey through the mystery of James Webb's impossible early galaxies, through the science and the speculation, through the observations and the theories, it's worth asking where we stand now, what we've learned, and what might come next in our quest for understanding. The answer isn't simple, because science rarely provides simple answers to complex questions, but there are threads we can follow toward clarity. The observations are solid. James Webb has detected numerous galaxies at high redshifts, confirmed through spectroscopy, that appear more massive and mature than our standard models predict for their age. This is not a measurement error or an artifact. It's a genuine puzzle that requires explanation. The number of such galaxies is larger than expected, suggesting this isn't just occasional statistical fluctuation, but a real population that our models failed to predict. Several possible explanations are being actively explored, and they're not mutually exclusive. The truth might involve combinations of factors rather than a single dramatic revision. Star formation in the early universe might have been more efficient than we assumed, converting larger fractions of gas into stars more quickly. Dark matter might have clumped more rapidly than our models suggest, creating deeper gravitational wells that collected matter more effectively. Supermassive black holes forming earlier than expected might have influenced their host galaxies' evolution in ways we haven't fully accounted for. There might also be selection effects we haven't fully appreciated, biases in what James Webb can detect that make the early galaxy population appear more massive than it truly is. But current evidence suggests this can't explain away the entire puzzle. Some genuinely massive early galaxies exist, and understanding them requires refining or revising our models of galaxy formation. The resolution will likely come from multiple directions. More observations, deeper and more comprehensive, will better characterize the early galaxy population and reveal whether the current sample is representative or biased. Better simulations with improved physics and higher resolution will test whether plausible variations in star formation efficiency or dark matter properties can reproduce observations. Theoretical work will explore whether modifications to our cosmological model, perhaps related to the Hubble Tension or other anomalies, might resolve multiple puzzles simultaneously. Within the next few years, we'll probably have a much clearer picture. The astronomical community is actively working on this, with multiple teams pursuing different approaches, checking each other's work, debating interpretations, gradually converging on understanding. This is how science works at its best, messy and uncertain in the short term, but reliably progressive over longer timescales, accumulating knowledge and refining theories through sustained collective effort. What seems clear is that the universe's history is richer and more complex than our models fully captured. The first few 100 million years after the Big Bang were eventful, with structure forming rapidly, stars igniting efficiently, galaxies assembling perhaps more quickly than we realized. This doesn't overthrow the Big Bang framework or require completely new physics, but it does suggest our detailed understanding of that era needs revision, and there might be deeper lessons. Perhaps the universe is trying to tell us something about dark matter, or dark energy, or the relationship between these mysterious components and the visible matter we can directly observe. Perhaps the early universe operated under conditions different enough from today that our extrapolations backward need more careful consideration. Perhaps complexity emerges faster than we thought possible, with implications not just for cosmology, but for our understanding of how order arises from chaos generally. We might also simply be learning humility, being reminded that nature is under no obligation to conform to our theoretical preferences, that observation trumps expectation, that the universe is full of surprises for those patient and careful enough to look. This is valuable knowledge in itself, a corrective to the hubris that can develop when theories seem to work well and observations confirm predictions. The moment we think we understand everything is probably the moment we're most due for a surprise. Looking forward, the mystery of early galaxies will eventually be solved. Maybe not completely, maybe not in every detail, but well enough that it's no longer considered a crisis or a fundamental challenge to cosmology. It will become part of the standard story we tell about cosmic evolution, another chapter in the universe's history, understood and integrated into our larger understanding. And then new mysteries will emerge, as they always do. Each answered question reveals deeper questions. Each solved puzzle exposes new puzzles beneath. This is not frustrating. This is wonderful. It means the universe is inexhaustible, that there will always be more to learn, more to discover, more to wonder about. Our descendants will have their own impossible observations to grapple with, their own challenges to meet, their own opportunities to deepen understanding. For now, we live with the current mystery, work toward its resolution, and appreciate the privilege of participating in this grand human project of understanding the cosmos. The impossible early galaxies are teaching us something, and we're learning to listen, patiently and carefully, to what they're trying to say. That's all we can do, and it's enough. Thank you for staying with me on this long, slow journey through cosmic time and cosmic mystery. Through nearly 2.5 hours of exploration and contemplation, we've travelled together from the present moment backward across 13 billion years to the edge of creation itself, to the cosmic dawn when first light pierced the primordial dark. That you've been here, listening, thinking, perhaps drifting in and out of sleep while the story unfolded, that means something, and I'm grateful for your company. We began with a question, a puzzle, an observation that challenged our understanding. James Webb Space Telescope detecting galaxies that appeared too massive, too mature, too well developed for how young the universe was when they formed. We explored what this means, why it's puzzling, what explanations might account for it. We wandered through dark matter and star formation, through computer simulations and scientific uncertainty, through the patient work of observation and the careful humility of not knowing all the answers yet. The answer, as honestly as I can give it, is that we don't yet fully understand what James Webb is showing us. The impossible galaxies are real, their challenge to our models is genuine, and multiple teams of astronomers and cosmologists are working to understand them. The resolution might come from better understanding of star formation efficiency, or from dark matter behaving slightly differently than we assumed, or from some combination of factors we're only beginning to appreciate. Or it might reveal something deeper, something that changes how we think about the early universe more fundamentally. But what we've learned tonight goes beyond that specific puzzle. We've learned about the nature of scientific inquiry itself, about how we handle mystery and uncertainty, about the patience required to understand complex phenomena, about the beautiful interplay between observation and theory that drives progress. We've learned about cosmic time and human time, about how we fit into the vast history of the universe, about the privilege and responsibility of being the part of the cosmos that asks questions about itself. If you enjoyed this slow drift through cosmic mysteries, if this way of exploring science and philosophy and wonder resonates with you, a like and subscribe helps these videos find others who might appreciate them. And if you're moved to share your thoughts in the comments, what struck you, what questions remain, what you're taking away from this journey, I read them all and am grateful for everyone. To those already subscribed, thank you for being here, for trusting these explorations, for being part of this quiet community of curious minds. Wherever you are in the world right now, whatever time it is, whatever brought you to this moment of listening and learning, I hope you're comfortable. I hope your breathing has slowed and deepened. I hope your body feels heavy and warm, settled into rest. I hope your thoughts have quieted, the urgencies of the day released, replaced by contemplation of larger patterns, older rhythms, the slow, patient turning of cosmic time. Look up at the stars tonight if you can. If the sky is clear and dark enough to see them, those distant lights, each one a sun, each one possibly surrounded by worlds we'll never see, each one part of a galaxy that's part of a galaxy cluster, that's part of the vast cosmic web that spans the universe. And beyond what you can see with unaided eyes, beyond what the brightest stars and nearest planets reveal, there are galaxies, billions of them, stretching away in all directions, some so distant that their light has travelled for most of cosmic history to reach your eyes. And some of those galaxies, the ones James Webb is puzzling over, existed when the universe was young and strange, when stars had just begun to shine, when the cosmic dawn was breaking across space like the first morning after creation. They're telling us something about that ancient time, about how quickly structure and complexity can emerge, about how the universe grew from simplicity to richness. We're learning to understand their message, slowly, carefully, gathering more observations, refining our theories, moving toward comprehension. In the end, what remains is not just knowledge but wonder, not just answers but deeper questions, not just understanding but appreciation for the magnificent complexity of existence itself. We're part of this cosmos we study, stardust contemplating stars, the universe becoming conscious of its own history and nature. That's extraordinary, miraculous even, worthy of awe and gratitude. Sleep well tonight. Dream, if you dream, of ancient galaxies shining in the darkness, of first stars igniting, of the slow, patient work of cosmic evolution across billions of years. Dream of telescopes seeing backward through time, of scientists working to understand the impossible, of mysteries waiting to be solved by those with curiosity and patience and care. Dream of the universe as it was in its youth, full of potential and promise, and as it is now, vast and structured and still full of surprises. Dream of your place in this cosmic story, small in scale but vast in significance, brief in duration but eternal in impact, part of the ongoing adventure of existence becoming aware of itself. Good night, cosmic voyagers. Rest well. The stars will still be there when you wake, ancient and patient, carrying their light across the darkness, telling stories to those who take the time to listen. And tomorrow, if you wish, there will be more mysteries to explore, more questions to ask, more wonder to experience in this remarkable universe we're privileged to inhabit. Sweet dreams, peaceful rest, and thank you truly for being here.